Okay, hello. Today I want to show you about mimicking numerical model dynamic using Fourier neural operator but with physics constraint. So physics constraint here, it's referring to physics information neural network. So yeah, FNO but with additional loss function that is a physics equation. Okay, let's begin. So actually, this experiment is inspired by this paper. So this paper they are using a generative adversarial network or GAN, and in the GAN in here it's not normal GAN, but they add some physics constraint like this. This is the equation they are using. Wait, I forgot about that. Okay, this is the original paper. Okay, here. So it's called moisture conservation equation. So basically it's like this. Q in here is the specific humidity. So there are moisture transport in spatial that in horizontal and vertical in here omega and horizontal u and v, and et in here is evapotranspiration, if I'm not wrong. Yeah, evapotranspiration, and P in here it's precipitation. Actually, if we rearrange them, all of these terms except ET. So ET equal the moisture transport in vertical and horizontal plus precipitation. And here, as you can see here, the only positive term in here is only ET. The rest of it is negative. So that's why I've already said that ET equals all of this. And yeah, this is important. The calculation of all of this is computed at the pixel level. But in my experiment here, I will not using a GAN. Instead, I will using a Fourier neural operator, but the physics constraint is the same with this paper. And actually, in the original paper, they are using a radar, land observation data, and era 5 data, the data from the ACMWF. And yeah, okay. So FNO here the FNO in here will be try to mimicking how the dynamic in the GFS dataset. Yeah, and one important thing is you see here Q is specific humidity, but in the dataset of GFS, I will just show you here. In the dataset of GFS, there's no specific humidity. Yeah. Instead, we have the relative humidity, temperature, and pressure. Actually, you see that UV, temperature, geopotential, and relative humidity here is repeated, right? It's because they are presented in different levels, and levels in here it's in the pressure. FNO in here will the output, the FNO in here, for example here, the output is U at the 1850 level, and V also in the same level, and temperature, pressure, and specific humidity. The FNO will resulting this dataset. After that, in the next run, it will be inputted to the FNO again. And what we concern in this experiment is actually it's just precipitation. So from the looping of this FNO input and output, we will get this several stack of the precipitation prediction. Oh yeah, and here you see, to get the specific humidity, we need the temperature, relative humidity. Wait, actually this is pressure, and pressure. So before we apply the physics consistency for the in the training data, we must check if our ground truth data really comply with this physics or not. And as you can see here, actually I'm using this script, check physics in here. And from that I got this matrix, and as you can see here, they are not really zero. Instead, it's 0.5 0.4 in here, 0.3, and etc. So that's why, instead of assume that the result of our FNO will really absolutely comply with the physics equation in here, instead I'll try to fit the level of consistency with the real ground truth data. That's why the physics laws in here, I try to compare XE in here is the ground truth, XI in here is the loss of the ground truth data, and X with hat in here is the loss for the predicted data. And for the real loss, it will be the combination of the physics loss and the normal loss of neural network. And yeah, actually in this experiment, I'm just using the bare minimum of dataset. You know that in for example in GFS dataset, and usually in one session of the in the one session running of the GFS dataset, usually it will predict, if I'm not wrong, it will be 7 days or it's around 7 days ahead. But in here I'm just using one session GFS prediction, and it's also only up to 2 days. So that's why in here I only have a limited dataset. So yeah, you can guess it. The result will be not that good, but actually it's quite promising from the pattern. That's why I make a video about this. Yeah, we only have a limited dataset in here. So let's see about the code. And in here, this is the generate data script. So as you can see here, this is a PyGrip. This is grip2 dataset. So we need to convert them first to a NumPy dataset like this here. And then this is the check physics that I've already tell you about. And in here, this is the training data. This is the training script. Here, this is just normalized and unnormalized. This is the physics loss function. Nothing special. And I've just apply the function in here. And maybe you wonder, where's the model? The model is only it's only this. In here I'm using a Fourier neural operator, but spherical. So the Fourier operator in here, it's special because we're using a spherical operator. And for the loss, actually, um, I haven't understand about this LP loss, but I've already tried using MSE loss, and the result is not that good. But when I try the LP loss, then for your information, LP loss is presented in the library of this FNO module here. When I'm when I've tried this, the result is better than when I tried the MSE. Here our physics laws definition. In this experiment, the effort is only 100, and as you know, we we only have limited data set, so that's why in here, despite I have only limited data set, but the total training for every effort will be 50 times. And yeah, usually if you're using a neural network, usually you will using a mini batch, but because I only have a limited resource, like you know, I've only using a mini PC in here, and my storage in here is only few gigabyte. That's why I'm only using around 58 data, and only using a single gradient. Yeah, I'm only using a single data for every training here instead of mini batch. And at last we save the data. Now also I also save every checkpoint when it reaches the new base score. And honestly, I don't want to run this script in this video because it will take around 3 hours to run in this mini PC. And this is the script to produce the prediction. And actually I've already tried this, and this is the result here. Okay, here this is the first time step. So this is the first output of the FNO, and then in here this is the second output. For the first prediction, as you can see, it's quite accurate, right? This is the ground truth. This is from the GFS dataset. It's quite similar. For the second time step, still okay, but there is a decrease in the quality of the prediction. Third time step, the quality is keep decreasing until you find at the 14 time step. I don't know why, but there's many heavy rainfall predicted in here, and I also don't know why there's some empty space in the rainfall pattern in the prediction. Yeah, that's why I said that the result is not quite good, but in the earlier time step, the prediction is reasonable, I think. And in my opinion, if I increase the dataset, for your information, I only using one session of GFS dataset in here, so maybe the model is not quite capture the pattern of how GFS dataset or how GFS dynamic works. And yeah, in next video I think I will I already in my previous video my project is about the turbulence because I'm stuck. Yeah, so that's why I continue my another project in here. Maybe in my next video I will update about this project when I using more dataset for the training, and also I also want to try oh yeah, for your information, the model in here is just one to one. So one image here, the input image here, no, wait. So for example, the data from this dataset here will try to predict the dataset in here in the next time step. And if you play this image, if you please see the right the right side of this plot. If you see the rain grown truth in here, there is some flow right here, especially in here. There is something like a cyclone in here, so there's some flow in the ground truth data. But if you see in the rain prediction, it's only just pop out, and yeah, it's the rainfall is just pop out from out of nowhere right here. It just there's no movement. There's no movement like in the rain, like in the ground truth data. Perhaps if I'm using perhaps if I change the scheme, so for example I'm using 4 dataset in here to predict one in here, maybe the model can catch the movement in this GFS dataset. Yeah, maybe. And yeah, anyway, I will update to you in my next video, or in my another video. I think that's all. Thank you. Bye.